Thank you to the staff who organized this special meeting and to audience who is listening to my presentation. My name is Pengli and I come from Beijing Jiaotong University and Eindhoven University of Technology. Today I'm very glad to be here to introduce my research. I want to thank my collaborators, Andrea, Professor Yang, and Luke. The topic of my presentation is an exact method for integrated optimization of subway operation strategy with asymmetric passenger demands and operating costs. Next, I will introduce my research from the following 5 aspects: introduction, model description, solving method, numerical experiment, and conclusions. First, introduction. In many modern cities, urban subway systems always play an important role for passengers. Let us take 4 subway lines in Beijing as an example, as shown in the left picture. These 4 lines connect the suburb with downtown. The right figure shows the passenger demand during the morning peak hours. We can see that more passengers go into the downtown because most of the passengers are commuters, and the working zones in Beijing are mainly located in the downtown area, while the residential zones are mainly located in the suburb. By the way, our numerical experiments are based on Yizhuang line, the last case in the right figure. In the case of asymmetric passenger demand, using asymmetric rail plans in different directions can flexibly guarantee service quality and save operating cost. In the conventional method, the procedure in planning rail traffic are performed sequentially, as shown in the right figure. Although each procedure can be solved more easily, some problems may occur. For instance, if we do not consider rolling stock constraints, the optimized train timetable may require more rolling stock than can be used. So, to achieve the system optimization benefits, we treat the optimization of multiple procedures as an overall integrated problem. Specifically, our study focuses on timetabling and rolling stock planning. That is, we need to determine the arrival and departure times of each service at each station, and we need to match all services with rolling stock. We also consider some aspects of the line planning and the computation of train speed profiles. In particular, we only consider the planning of line frequency in the line planning, that is, to determine the number of train services. For simplify, we next use operation strategy to represent the combination of the 4 procedures, and our research focuses on the asymmetric operation strategy. Next part, model description. Of course, I will give a brief description rather than introduce the specific mathematical formulas. Our model is based on a bi-direction subway line with 2 depots. There are S stations in each direction, and the train can turn back at station S and enter station S+1, or turn back at station 2S and enter station 1. Next, I will divide the proposed model into 3 parts to introduce. The first part is about the line frequency and timetable. In the subway system, the headways in peak and off-peak hours of each line are usually obtained from the network level. These can be used as input parameters when we optimize the frequency and the timetable in the single line. Then, by deciding which services use the peak headway and which use the off-peak headway, we can determine the number of services and get the headway between adjacent services. The second part is about the train speed profiles. In this part, we need to select a mode of speed profile from a known set in each segment. As shown in the figure, we use different colors to represent different modes of speed profiles in each set, to each mode also corresponding to a specific running time. In addition, the dwell time at each station is predetermined based on long-term passenger demand to ensure the safety of boarding or alighting passengers. With this headway, running time and dwell time, we can obtain the entire timetable. The third part is about the rolling stock plan. The calculation of the rolling stock plan requires the timetable information, specifically the departure times at station 1, S+1, and 2S. The output in this part is to match services with rolling stock and the connection method between services. As for the connection, as shown in the figure, there are 2 connection methods for 2 services in subway system. The first is the green one. It means turn back on the line, while the yellow one represents the connection through the depot. The green one is faster but has a strict upper and lower time bound for operation. Yellow one is slower, but generally only have a lower time bound for operation. The objective in this problem have two parts. The first is the service quality. We consider the passenger waiting time and passenger travel time. I need to point out that we use additional weight before the passenger waiting time, because passengers usually pay more attention to their waiting time than travel time. The second part is operating cost, including rolling stock utilization cost (CU), maintenance cost (CM), and energy cost (CE). The CU is a fixed cost for using the rolling stock. CM is related to the milestage and also includes empty running or the deadhead trip. CE is related to energy consumption, and we also take regenerative energy into consideration. We use the weighted sum method to combine service quality and operating costs. We name the proposed model as Integrated Optimization Problem, IOP in short. This is a non-linear mixed integer model. Here we use the figure to show the relationship between each part of the model. The yellow, green, red, and blue circles represent the formulations about the frequency, timetable, rolling stock plan, and the train speed profiles, respectively. The overlap between the circles creates new hybrid regions. Each of the new regions represents a new coupling relationship. This figure shows that our proposed model seems complex because there are many constraints with coupling relationship. Later we will use the graph when introducing the solving method. Precisely the next part. We first consider decomposing the IOP into simple subproblems. Specifically, when we enumerate the possible outputs about frequency, and we name each output a scheme, and we name each corresponding subproblem as scheme optimization problem, SOP in short. Compared with IOP, the yellow circle is removed in SOP because the frequency in SOP is a parameter instead of a decision variable. The decision variables of SOP and speed profiles and rolling stock plan. Then, if we can get the optimal solution of all SOPs, then the best optimal solution is the optimal solution of IOP. In short, we solve IOP by solving SOP. We propose a forward dynamic programming FTP algorithm to solve each SOP. I cannot go to the details because of time limit. Although each SOP can be solved by using FTP algorithm, it is also time-consuming if all the SOPs are solved, because we use enumeration to generate SOP. In this sense, we propose two speed-up techniques to reduce the computational time. The first is the pre-processing procedure based on scheme racking. We relax SOP to approximate linear model and use simplex to solve. We name the solution of the approximate problem as potentials, and the potential actually is no better than the optimal solution of this SOP. We rank all schemes or SOPs according to their potentials. Then we can solve all SOPs according to the ranked sequence. Then we propose two stopping criteria. The first is that if the potential of the next scheme or SOP is worse than the known best optimal solution objective value of SOP, we can stop the algorithm, as known best solution of SOP is the optimal solution of IOP. This is because we rank all SOPs according to their potentials. That is, the next SOP have the worst potential. The second stopping criteria is about FDP. Here we omit it because it involves some mathematical proofs. The next part, numerical experiments. We design experiments based on Beijing Yizhuang subway line. As we mentioned in the beginning of the presentation, the passenger demand of Yizhuang line is obviously asymmetric. There is 13 stations and 2 depots in this line. In the first group of experiments, we generate the Pareto frontier by adjusting the weight of service quality and operating cost. We want to see the performance of the asymmetric operating strategy under different objective preferences. As shown in the left figure, we found that the non-dominated solutions locally aggregate around several centers. We mark each center with a red circle. We guess this is because the rolling stock utilization dominates the operating cost. In other words, each center corresponding to a case of flip size. And the operating strategy are optimized around these flip size as weight ratio changes. Then, without loss of generality, we propose a new problem. In this problem, the rolling stock utilization cost is no longer considered. We designed this case to verify our guess, and also because some subway operators classify CU as infrastructure investment rather than daily operating cost. As shown in the right figure, the Pareto frontiers of new program is smoother. That is, when we do not consider CU, the asymmetric operating strategy can be designed flexibly under different objective preferences. Then, we compare the optimal solution obtained by our solving method with the practical operating strategy of the Yizhuang line in 2015. We solved the optimal solution of IOP and IOP without CU and compare them with the practical operation strategy. The practical operation strategy is marked with red dots in the figure. There are two red dots in the figure because the operating costs have two different forms depending on whether the CU is included. We can see that compared with the practical operation strategy, optimal or asymmetric operation strategy has better performances. We also design experiments to see the effectiveness of our speed-up techniques. The first is the scheme racking. We calculate the gap between the optimal solution of the first SOP and the optimal solution of IOP. It can be seen from the red box that the gap is very small, and the optimal solution can be directly obtained in some cases. In this group of experiments, about 111,000 SOPs are generated by enumeration, while the algorithm can be ended before 700 schemes. Last conclusions, also our contribution. As shown in this study, we formulate a MINRP mode to optimize asymmetric operating strategy on a subway line that includes 4 parts: line frequency, timetable, rolling stock plan, and train speed profiles. And we design an exact method to solve the proposed model. Finally, we design numerical experiments based on Beijing subway line to evaluate the proposed methodology. That's all. Thanks for your listening. Any questions?